Okay, my name is Kimball Germane. I'm a student at the University of Utah. My advisor is Matt Might, who presented last month. I do research in static analysis. My recent research is static analysis of probabilistic programming languages. And I've been using Coq a little bit more, so I'm going to talk about that. By show of hands, how many have used Coq before? A couple? Okay. So Coq is a proof assistant. And basically that just means that it will help you write proofs and it will check proofs. And that's very important when proofs get really long and complicated. It's really great to have the machine check them. Like there's a theorem in mathematics, the four-color theorem, which says that you only need 4 colors to color any two-dimensional map. And that was proved, not in Coq originally, but using machine-checked proof because there were tons of cases and basically the machine does a lot of bookkeeping for you. So Coq is a proof assistant, and what makes it especially powerful is what's called the Curry-Howard correspondence, which relates proving things and writing programs. The Curry-Howard correspondence says that types are theorems and programs are proofs. So when you prove a theorem, you're actually writing a program. So like for instance, if I were to write this, then we might interpret that as a type. We know, okay, so this is a function that takes things from A to B. But from a logical point of view, you could see this as, given a proof of the proposition A, this function produces a proof of the proposition B. That is what implication is. So Coq uses this to encode implication, quantification for all, negation, and or lots of things. So Coq is based on this small calculus called the calculus of inductive constructions. And the inductive thing is what we're going to see a lot tonight. Basically, when you want to prove something in Coq, you write a small inductive system. So like, so if I wanted to talk about ordered lists, say, I could say, given a type and, sorry. So this begins the definition of a system that will help me reason about what an ordered list is. And I write down axioms. Now I'll get to more of that later. That's just an example. But let's talk about data types. So we're going to define the data type for natural numbers. And so we do that. Inductive, nat. The set keyword says...
You want a chair?
Sure.
Sorry, you said with 2 covered up.
Nice. So nat is of type set, which means it's a data type, like we might define in Haskell. And the cases of nat are, we'll say 0 is a natural number, and the successor takes a natural number to another natural number. And so this is a unary representation of natural numbers, and we can type check this.
I think you still have an A or a B.
Oh, yeah, thanks. Heck, this is annoying. Okay, so when it type checked it, it said nat is defined, nat rect is defined, nat ind is defined. It defined a lot of things for us. Nat ind is the induction scheme for nat. That says if we want to prove something about all natural numbers, nat underscore ind will help us do that. And nat rec is short there for recursive. And so if we want to operate on natural numbers, then we can use its recursion scheme. So let's prove something about natural numbers.
How do you write down 3?
Okay, so good question. So we'll say example. 0 is just 0. Oops. I meant this. Eval. Okay, so that's 0. So that would be 1. And then 3 is just repeatedly applying successor. And Coq has syntactic sugar for working with natural numbers. Natural numbers are built in, but they're defined just like this. And so we can use just Arabic numerals for natural numbers. So what should we prove about all natural numbers?
Wait, sorry, are you saying that represents number 3?
Yeah, I should put a comment to that effect.
So,
So we can write. Now I've shadowed nat, so I'm going to actually get rid of my definition of it. And I'll print the built-in definition. And you can see it's just the same. And now, because they've defined syntactic sugar in the standard library, 0, 1, 3, and then 3. Okay, so anyone have a theorem we should prove about natural numbers?
associative.
For addition?
Yeah.
Okay, so let's define addition. So we can write functions in Coq. And if it's recursive, we'll use the keyword fixed point. And this will be add. So given natural numbers a and b, return a natural number. So we're going to pattern match on a. If it's 0, just return b. And if it's the successor of some number, I won't do that, then return the successor of add and b. Is that okay with everyone? Okay. And so now we might say theorem add is associative. So we say for all a, b, c, nat. Hold on a sec. I need a comma. Sorry. Okay. So when we state a theorem like this, we put a period, it goes into theorem proving mode. And so the top right of the screen, it tells us what our sub goals are. And basically we are working with the type checker at this point to construct and type check the proof for this theorem. So we write proof, and now we use a different language called the Coq tactic language. And this, it's pretty similar to like a mathematical natural deduction style. So we say, okay, if we want to prove for all A, B, and C some statement, some proposition, then let's suppose the A, B, and C are given. And you do that with the intros command. And so now it tells us above that long horizontal line, that's the context, the typing context. And we have our subgoal below the line. And so we could do this, let's say we want to do this by induction on A. So when we do that, we now get two subgoals. One of them is where A is 0, because that was the first constructor for the natural number data type. And to prove this case, I think it should be as simple as just appealing to the definition of add, which we can by the keyword simplify. And then when we have something equal to itself, we use the tactic reflexivity. Okay, so now in the second case, we have an induction hypothesis that was added to the context. And so we can use that to help us. So let's see what happens when we simplify here. Okay, so now we've got that inside, and it looks like our induction hypothesis fits that, doesn't it? Okay, so we can rewrite. So what we want is, on the bottom we've got two things that are equal to each other, and we want to rewrite one of them so that it is identical to the other. We use that with rewrite. And then reflexivity, because they're the same, and we've proved it. QED.
So is there a way to like it right now, like the step by step?
Yeah. So if we do print add the soak down there, that is the function that proves this property for natural numbers. You give it natural numbers, and it gives you a proof that the addition is associative on them.
Can you write this on board in math?
Write what on the board?
The theorem.
The theorem? Sure.
Or better, can Cock export that? Like what you
Cock might be able to export LaTeX. I'm sure there's a plugin somewhere. One of the great things about Cock is that you can extract programs, verified programs that you write, into Haskell or Racket or Scheme or OCaml. So I'm sure there's something for LaTeX. So in math, it's for all A, B, C in the natural numbers. What? Oh, I just wrote the same thing. Reflexivity. Okay. All right. So when we write functions like add, Coq has some restrictions because it needs to be able to verify that all programs terminate, basically. Otherwise, its logic isn't sound. So one of the restrictions, probably the most prominent, is that you can only recur on a subpiece of the arguments. So we recurred an add with n, but n is a subpiece of the argument a, so that's okay. So most languages that we use have non-termination, and that makes them unsuitable as use as a logic. Okay.
Question. So, for instance, that applies to reals. There's no inductive definition of reals.
Well, an inductive definition for reals, you could. No, not all reals, because certainly not all reals are computable. But like any way that we reason about reals, because we don't deal with infinite objects, we could probably encode it in Coq. So any method of reasoning we have, we could formalize. Okay. So, any other questions?
Oops. Could you write the proof of, like, I mean, so the line, how, as far as the proof in Coq, how would that relate to, like, the mathematical proof? Like, what do those 3 lines?
The 3 lines on the right?
No, between proof and QED.
Oh. What do these relate to in regular math?
Yeah,
Like if you wrote them on the board,
Just translate that to English.
Yeah, okay, so this is how the proof goes. We say, okay, so we want to prove for all A, B, and C natural numbers, addition between them is associative. So I'd say, okay, well, let's assume A, B, and C are given, and by induction on A. So when you learn induction in school, you say, okay, I have to do it for the base case, and then I have to say, if I know it for any given one, I can give it for the next one. And so that's, and we'll step through the proof while we do this. So when we say, okay, let A, B, and C be given, they get added to the context. Then we say, let's proceed by induction on A. And now this is the case where A is 0. And so we say, okay, is it true, according to our understanding of addition, that 0 plus B and then adding that to C is the same as adding B and C and then adding 0 on the left? And according to addition that we've defined, that is true. So we simplify according to it, and then we just say, it's obvious right here.
So doesn't simplify just run the program as much as it can?
Yeah,
That's kind of the idea.
yeah.
and then the
Good point.
reflexivity is just saying true.
It's saying
it's asserting that it's true.
if
Well-
2 things look the same on the equals.
Yeah, now here's the interesting thing. Equality in Coq is not built in. It is itself an inductive definition. So let's see what that looks like. Okay, so this says, given a type and an element of the type, this will tell you, this will give you a function. So like basically this defines a family of propositions. So if I was to, I might say, let's see. Check is the keyword to type check. So I can say, are 1 and 2 equal? And that statement has the type proposition. And you can see that Coq's syntactic sugar kicked in. Would you guys prefer that I turn off syntactic sugar so we can see kind of the base stuff? Or do you want to keep it on?
Let's turn it off for a minute. Let's see what
Okay.
it's actually.
Okay, so if we were to do that again, that's the object we're dealing with. And then let's look back at the definition of equality. So equality defines a family of propositions, and it has one way for that to prove a proposition true, and that is if you give it the same thing twice. That so we can prove that 1 is equal to 1. That object proves it. Okay, so back to the proof. A, B, and C are given. We proceed by induction, simplify. Now we can see it's not rewriting things for us. And then, now we're looking at the case, the inductive case. So we have an inductive hypothesis. We just simplify according to the definition of add. Add can recur once because it knows the structure that its first argument is a successor. And that gets it in a place where it looks a lot like the inductive hypothesis. So we rewrite, they're the same. And so basically reflexivity all it does is calls the EQ underscore reflexivity with the first argument, and because they're the same, it is a proof for it. Okay, any questions before we go on?
So, can you go over this program? I don't know if it's helpful to go over this program.
Neither do I. I think I want to turn on
Yeah, maybe if you turn on the...
notation.
I always thought it'd be funny to go to a math class and turn this in. So here's a proof of that.
Yeah, it's... Do you guys
I
want...
guess you could explain it, because it just calls nat induction equal reflexive.
Yeah, okay.
It's all those functions, right?
Yeah, I'll go over it real quick. Okay, so let's print the induction principle for natural numbers. So basically, if you have a proposition over naturals that you want to prove, then if you give it a proof for 0 and a function that takes a proof for a given natural number to a proof of its successor, then it will give you back the proof for all. And so when we look at add associative, it basically, we have the natural induction. It needs a proof for 0 and a proof taking a number to its successor. So the first one, yeah. Okay, so this first argument is a proof for 0. That when a is 0, these are the same. And they're the same simply by reflexivity. And this next argument to nat ind is a function that given a natural number and the hypothesis that takes the proof for a natural number to the proof for its successor. Let's see. It does it by so this is the simplification step. And then reflexivity and using the hypothesis. Unfortunately, the order's not the same with how we did it, but if you wanted, you could, every piece is there. You could write in the proof yourself by instead of putting a period, you can actually give the definition of the proof right there. And so oh, wait. And then if we were to instead say all right, sorry. They are the same. Okay.
So, I have a question. Why are there ones in the type? It seems kind of weird that there's data in the type.
Oh yeah. Coq is a dependently typed programming language, which means the type of a function can depend on its argument, and we'll come to that more later. All right. Okay, so now let's talk about the predecessor function. So I'm going to try to do it without those, but those are just in case. Okay, so the predecessor function over natural numbers, it's pretty simple. Oh man, want to hide that.
Just a quick question. So you said they're strongly normalizing. That means that you ultimately arrive at the base case. Is that?
Ultimately what?
It use the term strongly normalizing. It means that, am I interpreting correctly as saying that means that you ultimately arrive at the base case?
Yes. Yeah. So, and that's just, I guess, the fancy way of saying all programs terminate. You can't write a non-terminating program. Okay, are you guys happy with this definition? Anyone unhappy with it? Yeah, why?
Well, 0 is not less than 0.
0 is not less than 0. What should the predecessor of 0 be?
I don't know. We haven't defined that.
Bottom or something?
Yes,
Error bottom?
Error, bottom. Bottom might be interpreted as non-termination, a diverging program. What if we said, you can only call this function if you hand me a proof that the argument you give me is more than 0? Okay, so actually before I go into that, I skipped over some stuff. So let's talk about negation in Coq.
I think you have a type. Shouldn't be on prime answer. Or
Oh yeah. Well, we weren't going to prove any theorems about it. Yeah, n prime. Okay, so Coq uses constructive logic, which means the law of excluded middle, that for any proposition, either it's true or its negation is true. That's not part of it. Basically, you need to give a proof object that proves your proposition. So how do you prove negation in that framework? So what Coq does is they say, let's look. Okay. First, here's the notation for negation. It's not the case that 1 equals 2. And then in the goal there, not equal is just the less than greater than. And I don't want to prove this, so we can write admitted. So admitted is Coq's FFI, basically. And it's an FFI to a pencil and paper. And so it's pretty dangerous because it's great to have the machine check your reasoning for you. So let's look at what the notation. Oh, not. So that's just short for not. So let's print what not means. So when you negate a proposition, you're saying that that proposition actually implies false. And true and false in Coq are defined inductively also. True is the proposition that it's trivial to give evidence for it. It has one constructor. All you have to do is say I is proof for true. Anyone have any intuition of what false might be? False is defined as something which you cannot give evidence for. There's no constructor. So this is actually a really clever encoding of false because it allows us to use common logical rules like false implies anything and that contradiction implies anything. So basically, let's go back up here. When we say 1 does not equal 2, let's unfold not. And what we're really saying is that the proposition 1 equals 2 implies false. If someone gives you evidence that 1 equals 2, then you can give evidence for false, or at least that's what we're supposed to prove. So when we have an implication in the goal position, we can we use intros H. That's like saying, okay, we want to prove that 1 equals 2 implies false. We'll assume 1 equals 2. And then what is the natural way to say, well, we know 1 is not equal to 2, according to how natural numbers are built up? 1 is less than 2.
Reflexivity, I mean, they don't match up.
Yeah, they don't match up. So the way that we say, check the arguments whether they match, is inversion. So if we say inversion H, basically this compares things on the left-hand side and the right-hand side of the equal sign. If they were built from the same constructor, then it adds sub-goals for all of their constituents. But if they're not built from the same constructor, then you have a contradiction and your goal is proven because false implies anything. Okay, so we just proved that it's not the case that 1 equals 2.
So you can change that.
Yeah, it doesn't matter. Okay, so now back to predecessor. So we want a predecessor function where we require a proof that the argument is greater than 0, and then we'll give the answer back. So given a natural number, we'll say we return a function that takes okay, so this says return a function, given a natural number, return a function that itself, when given proof that n is greater than 0, return a natural number. So we match n with, okay, now we're going to write a function, we're going to have some argument and some body. And this argument is a proof that 0 is greater than 0. Yeah. Okay. So what should we put here? We'll just put dots here for now. And then Sn prime is simple. It ignores the proof and returns n prime. Okay, so let's prove a little theorem real quick. That 0 is not greater than 0. Okay, so proof unfold not H. Actually, before I do that, okay, so greater than is syntactic sugar for less than, and less than is syntactic sugar for less than or equal to. And now we can introduce the hypothesis. And the induction scheme for less than or equal to, I think, will just tell us right off that that is not the case. Okay, so we've proven this.
So unfold is basically just rewriting it? Like
Yeah, unfold just looks at the definition and replaces it and substitutes arguments and everything.
Would you have needed that?
I don't think so. I just wanted to illustrate what was going on. And so if we print this, what does a program of the type not 0 greater than 0 look like? What kind of an object are we gonna see? Well, okay, so negation is actually implication of false. implication is a function. So we would expect this to be a function that, given a proof that 0 is greater than 0, returns a proof of false. That's what that looks like. So we should have just written that, actually. So-
What is that showing us?
This is an object
Oh,
of type not 0 greater than 0. And it's a function. I'll scroll up so we can see it's a function. And yeah. Okay, so, but that wasn't just for fun. So now we have a function that we handed a proof 0 is greater than 0, and it hands us back an element of false. So we can apply that function and match on it. So the type of this parenthesized thing right here is false. So we have to write a case for every one of its constructors. False has no constructors. So that's what we write.
So is there syntax sugar to do that? Because I imagine you have to do things like that often.
Yeah, there is. So yeah, we're going to get into that right now. Okay, so this is good, but it could be better. Any suggestions? Yeah.
Do you not just have a partial function there that only takes successors? If it's successor, then it's match, otherwise.
Yeah, and I think in a kind of a roundabout way, this is that. And there are cleaner ways to do it. But to my knowledge, I don't know that you could write, we couldn't just write S here, given something built with constructor S, or maybe even like S of n. But now we're kind of getting into dependent types, where the type of the result depends on the type of the argument, or on the value of the argument. And so it would be nice to encode the correctness of our predecessor function in the type, because that's what we use types for, right? To do, to encode our reasoning. So let's build up to that. Okay, so we've got, in Coq, we've got universal quantification, which is for all, and existential quantification, there exists, is defined in terms of it. So this says, given a type and some proposition over that type, then you can prove there exists an element that meets that proposition if you're handed a proof for a given element. So like we might say, you could say there exists a natural number n such that n equals 1. And then when we're proving it, it's really simple. We say exists 1 reflexivity and then this proof, it has a function that takes natural numbers to the proposition that that number equals 1, the witness element 1, and the proof, which was just reflexive equality, or the reflexivity of equality. So there's something very similar to it called, very similar to EX exists, called SIG. So EX exists is what we would use when we're dealing with a theorem, but when we're trying to write a function, we use sig. Sig is more suited to that. And its definition is very similar. So here's a way of writing, rewriting our predecessor. We could say oops. Let's do that now. Okay, let's do this. Okay. Should I parse this? Okay. So our next predecessor function doesn't take a natural number. It takes a pair of a natural number and a proof that it's greater than 0. And that pair is encoded in this type, sig. We specify that the first element is a natural number. Here is the function that takes a natural number to the proposition. And yeah, and if we want to produce an element of this type to give to pred2, we have to also include a proof that this proposition is true. So we match S. Just a sec. What did I forget?
You might need parameter on S.
0, not 0 greater than 0. Okay. So this function, pred2 and pred1, are essentially the same, at least in what they're doing. But just in pred2, we say instead of giving us, instead of like currying, give us the number and then give us the proof about the number, we're saying give us a pair that has the number and the proof right there. So with this in hand, and there's notation for this that probably makes it a lot easier to understand. So let's, oh, we're displaying notations. Okay, so it's really ugly on the left, but the type of this function is actually a nat n, such that n is greater than 0, returns a nat. So now here's the final iteration of our predecessor. Given S such that it should return a natural number m so what is the correctness criterion for predecessor? How do we know that our predecessor function is correct given, what's the input-output behavior?
SM.
Yeah. And so S is a pair. We get the first component out of it with this, equals, and the result okay. Are we happy with that so far? Okay.
And isn't defined out of that scope just, and it's just defined for as a type of S. So we can't say M equals SM.
Yeah, but S is in scope, so we have to pull it out. Okay, so oops. S, this is going to be exist. And if instead it's a now, what goes here? And maybe it's simple as this. It's all right. I have a contingency for just this, which is then defined already. Okay, so this is pred 3. I didn't use syntactic sugar for it, and it's not very illuminating. But essentially, this is, if you didn't want to use really any of the facilities of Coq to make it easy to write these things, if you wanted to build the proof objects and types yourselves, this is what it would look like. And this is just slightly better. This return I've added hints to the type checker in Coq, and so we can put wildcards and it will infer the type. But anyway, so pred 3 is a fully specified predecessor function, and you could extract it to OCaml. And kind of the funny thing about the OCaml extraction for all of these programs is that they're all the same. The proofs get erased when you extracted those programming languages. But if you were to extract a whole program, you would get the guarantees of this type system, and then you'd be fine. Are there any questions? Yeah.
How do you actually call one of these?
Oh, yeah. I've got an example of that, I think. So when we call pred 3, we have to give it an existence proof that I have this 2 is greater than 0 right here, which I'm just going to admit it. I was going to prove it, but
Yeah. Double definition.
maybe. Need to admit. Okay, so I hand it a pair of the number 2 and the proof that 2 is greater than 0. And it hands me back. You can see a 1 in there. And then a lot of other stuff, a lot of other guarantees. All right. Okay, so there are tons of resources for Coq, and they're much better than I am for introducing it. The reference manual is pretty good. I've heard Coq Art is great, I don't have it, but Certified Programming with Dependent Types is excellent, as is Software Foundations. Those are available free. And then I wanted to talk a little bit about some cool projects that are being done with Coq. VelVM is verified LLVM. So yeah, that's kind of just what it sounds like. A verified software toolchain and Why Not are frameworks to reason about C programs and imperative programs. Bedrock is reasoning about assembly language. There are some verified kernels that are fully verified, and CompCert is a gigantic project which aimed to have a formalized C compiler, and they succeeded. And one of the researchers at the University of Utah, John Regier, they basically do like hardening for compilers, and in a lot of they were doing like fuzzing and stuff for C compilers, and CompCert had the fewest number of bugs, and the only bugs it had were in the unverified parts, which was the parser, the front-end parser. And since then, that project has verified their front-end parser. So there's good reason to think that there are not mistakes in CompCert. Yeah. Like, did you raise your?
Yeah. What kind of things are they proving? You know,
They're,
what are the properties of the compiler that they're proving?
Yeah, so they define the semantics for C and the semantics for assembly, and their high-level proof is that the semantics are preserved across compilation. But the chain it includes register allocation, so it has stuff about graph coloring. It's on their website. There's a really cool diagram that shows all of the phases that they've proven, and it's awesome. So that's what I have. Yeah.
Just a question on what you showed earlier about the predecessor way of passing a proof of, say, that the number is greater than 0. Are those proofs, or the need for those proofs retained even when you extract the code to say OCaml? So they get it widespread.
Yeah.
Like that.
Yeah. But like Idris is a dependently typed programming language that's kind of getting more popular, and I wonder if they would extract to Idris differently, where you had to provide a proof.
Can you go back up to that code you were writing to give them?
Yeah.
Yeah, that one.
Yeah.
So it seems to me that you're writing the same code. So in your definition, you're saying S natural number such that n is greater than 0, but then you're matching on S, which is 0. So why are you needing to look for S if you're already proving that it's already greater than 0? Why do you need that?
Why do I need this first match clause? I think to satisfy the exhaustiveness check of Coq. There might be a way to write it without it.
I think you're getting at an interesting point, though, that like if you specify something so much that you've given an implementation for it, it's you kind of have to write everything twice. So, and that happens with type systems to a certain extent too. You're writing your program in types, and then you're writing your program in code. And if because you can make the types so specific that they're actually code as well, you can end up in that situation.
So in this case, wouldn't you come up with a new type called NAND plus, say that's a positive number to start off with?
You could.
Straight to.
Yeah, and then to be allowed into that type, to build an object of that type, you would have to give a proof that the natural number you were handing it was greater than 0.
Well,
Or even be a
just-
natural number, I'm just saying you wouldn't pass in natural numbers, you would be passing objects of type, nat,
To nat?
whatever.
Oh, yeah.
A new type that just doesn't include 0 at all,
Yeah.
right?
Yeah, that's a way to get around it.
Are there certain classes of proofs that Cockpit works on with their own? Like I'm thinking like if you're trying to prove some parametric identities that relies on geometry, the congruency of two shapes, that just seems like, I mean it's easy to see it, right? Like when you're drawing on a piece of paper, but here like you claim that it seems I don't know, like I'm trying to see like if that would be helpful or like
Yeah. The foundation for Coq, which there's a lot of stuff built on top of the foundation, but in a sense we're still pretty shallow, is extremely rudimentary. And so the odd order group theorem was recently proven, and it required them to formalize tons of seemingly unrelated math for it. And so there's a comparison of different proof assistants online that they were asked to prove that the square root of 2 is irrational, and some of them appeal to like a geometric thing and they encode what I guess their intuition is about the geometric object, and so that's pretty interesting. If I'd look at that.
I have another question.
Yeah. Okay.
What do you think it's a good like tool for teaching proofs? Or yeah, I'm just wondering because we were just actually watching Scott and I we saw this presentation by Gerald Sussman where he talks about how programmers can use math better, programming to understand math better. Like he's writing all these derivative stuff and speaking, and it just makes more sense to a programmer that way. I'm wondering like. You see Coq as a way of like as a programmer you can understand proofs better? Or do you think it gets in the way a lot of the time?
Yeah, would it be better to learn inductive logic through inductive logic or through Coq or programming?
I think through Coq, definitely, because I think I would have loved this when I was younger and I wanted to understand what was really going on with proofs, because you can look at the proof objects and you can see that you're actually building a proof, like the proof is what you might write with a proof tree if you had a list of inference rules and everything, and you can look at it and you can see how they fit together. I think that for most, like for functionally inclined programmers, it would be an excellent resource to learn. And the Software Foundations, that book, is a very gentle introduction to proving with Coq. It's a great book. Yeah, it's fantastic, and it's free. So
But what assumptions do they make about the background for the reader?
very, very little. It'll explain the rules of logic, and it'll step through proofs and explain in plain English what's going on, and then what you're doing in Coq. It's great.
And it goes through developing a whole like programming language later on.
Yeah.
So, which it's actually interesting. Like numbers are actually a lot harder to do things about than programming languages are.
Yeah.
Like you can do proofs about programming languages that are easier than proofs about numbers.
Mm-hmm.
And these are just natural numbers, like doing proofs about other kinds of numbers is even harder.
Yeah. About a week ago, Blake and I were at a static analysis seminar, and we decided to formalize one of the soundness proofs for a really basic static analysis, and it still was pretty intense. We had to go into a lot of detail. Cool.
So one less comment,
Yeah.
sorry.
No.
But so there was a project where they formalized SQL in Coq, and so you had a little SQL interpreter that was proven correct, so none of your queries are ever gonna give you the wrong answer. and they proved that it was equivalent to relational algebra. But they gave, in the paper, I think they gave like what percentage of their code was actual programming and what percentage was proof, and like the time they spent on it. And I think the proofs were like, I want to say like 80% of the code and time. So actually writing your program is easier than writing all the proofs that surround it when you're doing stuff in Coq.
And then one last thing I'll point out is these were the most popular projects I could find, and I think it's interesting that every single one of them has to do with basically imperative languages or assembly languages. There's not much, at least in terms of verifying, of like functional languages, but I just thought that was interesting.
There was a project that I saw the other day. I thought it was, I can't remember the name. It started with R. It was for distributed systems. Like Matt might recreated. You know, I think it was one of his friends working on it. Like, right? Did that sound familiar?
They're formalizing it in Coq or something?
It was it was something built on top of for distributed systems. And I wanted to say it's called Reflect, but we've been using Reflect here, so maybe.
I'm not sure.
Okay. Because yeah, that'd be interesting, right? A good use case of something like this. Distributed systems.
Yeah. Okay.
Sorry, quickly.
Oh, no.
Is it used for like protocol verification as well? Or
Yeah, actually, like cryptographic protocol.
yeah, for instance, yeah.
Yeah, my former advisor and Blake's advisor, Jay McCarthy, who presented here, his PhD used Coq to verify that certain cryptographic protocols composed and were still secure. And so, yeah. I think it's an expressive enough logic that pretty much any reasoning you could do, you could encode in Coq. But, I mean, that's not strictly true, because it's got to be incomplete. That's what Gödel told us. But anyway. Okay, that's what I got.
The statement cannot be expressed.
That can be expressed but not proven in the logic.